Alright, so we ended the last video by talking about refraction, so now we're going to talk about diffraction. So refraction is when you bend when you go into a new medium. Diffraction is when you actually bend as you pass through boundaries. So we first looked at this by looking at Young's double slit experiment, which is basically a screen that has slits in it, and when you shine the light at this screen, the light then bends through these two holes and then is collected over here on another screen. And on this screen we begin to see interference patterns, which are essentially bright and dark fringes. So the bright fringes are where we're seeing some constructive interference, and the light that is bending through each one of the two different slits is actually arriving in phase or at the same time and constructively interfering, meaning that actually what is happening is that one wave is traveling one wavelength further. So the equation that we can use to sort of figure out the location or discern something about this type of experiment is this, which is that d, which is the distance between the two slits, times the sine of the angle, where this is the angle here. It's the angle from a line that goes straight from the screen or perpendicular from the screen to the other screen to the location of the bright fringe over here. So quite frequently we know the distance between the screen and the collector, and then we can measure over here where that bright fringe is, and then that will give us that angle. M is the order number. That's just the fringe number. We say order maximum, which is where you've got your bright fringes. So the first one is called 1, the second one is 2, the third one is 3. And then over here, the first dot would also be, so this would be 1, and this distance really should be the same as this distance, and the angle should be the same there. And then that's obviously the wavelength of light over here. So if we want to calculate something about the dark fringes we're going to have destructive interference, so the waves are arriving out of phase, meaning one of the waves has traveled half of a wavelength further than the other. So here we use the same equation, but we have d sine of theta is equal to m plus 1/2, so the order number plus 1/2 times the wavelength, and that will allow us to find what is called the minimum or the destructive fringes or the dark fringes. Alright, so there's lots of different things that we can do to sort of like manipulate this experiment and see how, the angle or the position of the fringes changes. So if the distance were to increase, so if you were to move the distance of the slits apart, the distance would get greater. So in order for this to remain the same right here, that means the angle here would actually have to decrease, so that the sine of that angle would be smaller. So the fringes actually get closer together if you spread the distance of the slits apart. If the slits get closer to the screen, then the fringes are going to spread out. So if I move this thing closer, or change what is like this variable L, essentially as it moves closer, this is going to keep going out and out. So you can, maintain the same ratio of this to this and have the same sine of the angle there, right? Now, other than double slits, sometimes we use something called a diffraction grating, which is basically just a transparent material that has a lot of different scratches, often a lot of scratches on it, and it's used to determine the wavelengths of light frequently. So it's really the same equation as the double slit experiment, but typically diffraction gratings you're told how many lines or how many scratches there are per distance measurement, so it's like lines per meter. So if you want to get the d that is for the equation, then you have to take an inverse of that number. So taking an inverse of this number will give you d for the d sine theta equals m times the wavelength. But everything else is the same, the interference patterns and the order numbers, and we only really use this one. Typically we're looking for bright fringes there. So that can allow us to figure out the wavelength of the laser like we did in the lab. Right? So then the last thing we really talked about was thin film interference. So it brings back that idea of interference patterns. So when we have constructive interference, we're going to see bright, and destructive interference is when things are going to get dim. Also, it has us looking at the index of refraction and phase changes when things reflect. So just as a reminder, when you have an N1 right here that is less than the N2 that it's going into, we're going to have a phase change. right? If we have a case like this where we're going from an n2 that is, well, this n is bigger than this n, then we see no phase change. I don't want to write the n's up here because I think it'll get confusing, right? Now, as the light comes in and it bounces off, here's my angle of incidence. And remember, there's going to be some transmission and some reflection. So the reflection is going to be equal to the angle of incidence. And when this thing bounces off, because n1 is less than n2, we're going to see a phase change in that ray. Some of the light is going to pass into this new medium. The index of refraction is greater, so the angle of refraction is actually going to be small. It bends towards the normal. This thing slows down. As it slows down, it's got a new wavelength, right? Wavelength in that new medium is equal to wavelength over n. Right. And then, as it encounters this interface, it's going from a big index of refraction to a small index of refraction. So here's my little angle of incidence now, and it bounces up like this, angle of incidence there, and then when it escapes, it goes like this. But on this bounce right here, there's no phase change. Right? And then here, some of that light goes down and into this medium, and it's going to go back to the same angle as it was here because it has an n1 there, right? But the question is like, how are we going to make these two things constructively interfere if by their reflection patterns they are phase changing? So we can determine the thickness of this film that it would have to be so that those two reflected light would come and be in phase again. Right? In order for this to do this, because one is phase changing and the other is not phase changing, we've got to make this thing move 1/2 of a wavelength further in order for when it escapes, it's going to be in phase with this together. So the thickness of the film has to relate to the wavelength by being 1/4, so it can go down and back up and have traveled 1/2 of a wavelength further than the other one. Right? So for this, when you have a phase change and no phase change, we say 2nt is equal to 1/2 of the wavelength, right? So this really just means the thickness of the film is 1/4, because I'm just dividing by this 2 over here, the wavelength of the wavelength in the new medium, right? So these two equations are the same. So for down here, when we go from an index of refraction that gets increasingly bigger, an n1 to that's smaller than this, it's going to bounce back up, and we're going to have a phase change here, right? And this one, when it reflects off here, because it's this going from a small to a large index of refraction, we're going to see a phase change as well. So in order for them to come out of sync, right, this one has to move some increments of, one wavelength further. So we're going to make the thickness of the film actually equal to 1/2 of the wavelength. So as it goes down, it travels 1/2 of a wavelength, then it goes back up, it travels another 1/2 of a wavelength, so now it's traveled 1 full wavelength further. So when it pops out over here, then these two things are going to be in phase. So for that, we say 2nt is equal to wavelength, right? And let's solve it out like we did this. It means the thickness of the film is equal to 1/2 of the wavelength in that new medium. Right? So that is thin film interference and diffraction, and the rest of optics.